this module, you will learn about the deviation of real gases from ideal gases. Gases that obey the ideal gas equation are called ideal gases. The ideal gas equation is PV equals to nRT. If we plot a graph of PV versus pressure at constant temperature, then, according to Boyle's law, we should get a straight line parallel to the x-axis, as PV is constant at constant temperature for a fixed amount of gas. However, for a real gas, we find that the plotted line is not a straight line parallel to the x-axis. This shows that real gases, which include almost all the gases such as nitrogen, oxygen, hydrogen, and carbon dioxide, show a significant or an appreciable deviation from the ideal gas behavior. When we draw a plot between PV and P for these gases, we get two types of curves. The curves for hydrogen and helium, as shown, lie above the ideal gas curve, and these two gases show a continuous increase in PV with the increase in pressure. Whereas, for other gases such as carbon monoxide and methane, the PV value first decreases with the increase in pressure and reaches to a minimum. Then, this value increases with the increase in pressure so that it crosses the straight line of the ideal gas. Thus, a negative deviation is observed initially in the curve, followed by a positive deviation as shown in the graph. Let us observe the nature of the graph obtained for a real gas in a pressure versus volume plot. It is clear from the graph that at very high pressure, the volume occupied by a real gas is more than the volume occupied by an ideal gas. And at very low pressure, the volume occupied by both a real and an ideal gas are almost the same. Hence, at high pressure, these gases significantly deviate from the ideal gas behavior. Dutch physicist Johannes van der Waals gave an explanation for these deviations and modified the ideal gas equation in order to make it applicable to real gases. He observed that at low temperature and high pressure, the following two assumptions of the kinetic molecular theory do not hold good for the real gases. Assumption 1. There are no forces of attraction between gas molecules. Assumption 2. The actual volumes of the gas molecules are negligible when compared to the total volume of the gas. Let us see how the first assumption is modified and made applicable for a real gas by van der Waals. If the first assumption is correct, then the liquefaction of the gases wouldn't be possible. But we know that gases can be liquefied by decreasing the temperature and increasing the pressure. At high pressure, molecules of gases are very close to each other, and the intermolecular attractive forces start operating. These molecules then do not exert full impact on the walls of the container as they are dragged back by the attractive force of other gas molecules. Hence, the molecules strike the walls of the container with reduced velocity. Thus, we can say that the pressure exerted by the real gas is lower than the pressure exerted by the ideal gas. Hence, the pressure in ideal gas equation is corrected as P ideal is equal to P real plus A multiplied by N square divided by V square, where N is number of moles of the gas, V is the volume occupied by the gas, and A is the proportionality constant characteristic of a gas. In the second assumption, the actual volume of the gas molecules is negligible when compared to the total volume of the gas, which is valid only at very low pressure. But at high pressure, the molecules are restricted to move around in less volume, and hence the volume occupied by the molecules themselves becomes significant. Hence, the volume V in ideal gas equation is corrected as ideal volume minus the volume occupied by gas molecules, that is, V minus B, and for N moles of the gas, it is V minus NB. B is excluded volume, which is constant and characteristic for each gas. After substituting the two corrections of pressure and volume in the ideal gas equation, PV is equal to nRT, we get P plus AN square by V square multiplied by V minus NB is equal to nRT. This equation is known as van der Waals equation. Here, N indicates the number of moles and the constants A and B are called van der Waals constants. The values of A and B depends upon the nature and characteristics of a gas. The value of A is independent of temperature and pressure. The extent to which a real gas deviates from an ideal gas can be measured in terms of the compressibility factor Z. It is defined as the ratio of product PV and nRT. For an ideal gas, the compressibility factor Z is 1 at all temperatures and pressures because PV is equal to nRT. On plotting a graph of compressibility factor against pressure, we get a straight line parallel to x-axis at very low pressure. We find that at very low pressure, all gases have compressibility factor approximately equal to 1 and behave like an ideal gas. At high pressure, all the gases have compressibility value greater than 1. This means that these are very difficult to compress. At intermediate pressure, most of the gases have compressibility value less than 1. This means that these are easily compressible. Thus, we can conclude that real gases show ideal behavior when the volume occupied by them is so large that the volume of the molecules can be neglected in comparison to it. Hence, we conclude that the behavior of a gas becomes more ideal when the pressure is very low. The magnitude of this low pressure varies for each gas as it depends on the nature of the gas and the temperature. The graph shown here depicts the effect of temperature on the deviations shown by a nitrogen gas. The temperature at which a real gas obeys ideal gas laws over an appreciable range of pressure is known as boil temperature or boil point. The boil point depends upon the nature of the gas. The boil temperature of nitrogen is 332 Kelvin. Above boil temperature, real gases are difficult to compress and the Z value is greater than 1. Below boil temperature, real gases first show decrease in the value of Z, then reaches minimum, and with the increase of pressure, Z value increases continuously. Thus, at low pressure and high temperature, gases show ideal behavior. Let us see another significance of the compressibility factor. We know that compressibility factor for a gas is calculated as Z is equal to PV real divided by nRT. If the gas is ideal gas, then V is equal to nRT divided by P. On substituting the value of nRT divided by P in the equation for compressibility factor, we get Z is equal to V real divided by V ideal. From this, we can conclude that Z gives the ratio of the actual molar volume of a gas to the molar volume of it, if it were an ideal gas at that temperature and pressure. You have now reached the end of this module. In this module, you learned that an ideal gas is a gas that obeys the ideal gas equation, PV equal to nRT, under all conditions of temperature and pressure. Real gases do not obey the ideal gas equation at all conditions of temperature and pressure. Dutch physicist Johannes van der Waals gave an explanation for these deviations and modified the ideal gas equation in order to make it applicable to real gases. The van der Waals equation is given as P plus AN square by V square multiplied by V minus NB is equal to nRT. The compressibility factor for ideal gas is 1, as the ideal gas equation is PV is equal to nRT. The temperature at which a real gas obeys the ideal gas law over an appreciable range of pressure is known as the boil temperature or boil point.